Okay, everyone, let's work on a cone. So we have the tank in this problem filled with water in the shape of an inverted cone, so upside down cone, or point down cone. How about if I say it that way? I don't know what's upside down or right side up. So it's a cone with its point down, its circular basis at the top. It's 20 feet tall and its radius is 5 feet. Okay, so here's one again where in fact, even more in this one, I think. A picture is helpful. Okay, so we have our cone. Let's read the rest of it, and then we can decide what's fixed and what's changing. Water is coming out of the bottom of the tank, okay, at a rate of 2 cubic feet per minute, okay. And we want to figure out how fast the water level is falling when the water is 8 feet deep. Okay, so we have the water at some point in this tank. It starts off full, but it's not going to stay that way. In fact, it's for sure not that way. We're interested in when the water's 8 feet deep, so this actually looks a little high. So let's walk through and look at all of our info. We're given the height of the tank is 20 feet. That is not going to change. The depth of the water will change, but the height of the cone actually does not change. So that one, you don't need to give a variable name. You can just label that right in your picture. 20 feet high. The radius of the cone is 5 feet, and that as well is not changing. The tank isn't changing size. It's the water that's changing. Okay, we've got this 2 cubic feet per minute. I labeled it here in my picture, but let's actually give it a derivative name. That's definitely a rate of change, right? Cubic feet per minute. So if we take that 2 feet cubed per minute, once again, I think units should be a really big key here. Cubic feet is a volume, so this is a dV dt. But we actually want to be a little extra careful here. I am infamous for forgetting to be careful about this, but the good news is you don't get in too much trouble if you forget. I'm saying now that V is the volume of the water in the tank, right? So this is how much water is in the tank, and T is time in minutes. And my problem is that the amount of water in the tank is decreasing. So this should actually be a negative. The good news is, if you were like me and you forget to even think about if that's positive or negative, you'll just get the wrong sign at the end. So if you're looking at your answer and it says something is decreasing and you think it should be increasing or vice versa, you might want to go back and think about if these values had the wrong sign. So it won't give you the wrong number, just the wrong sign, wrong direction. Okay, we want to know how fast the water level is falling. So I am going to call the water level, I'm going to call it H. You can call it whatever you want. Labeling in the picture counts as defining your variable. Otherwise, do make sure you write it out in words. So we want to find how fast that's changing, dH dt, when H is 8 feet. And here it is really important that I don't put the 8 feet in my picture and just assume that the water is 8 feet deep all along. The point of this problem is that the water level is changing, and we just want to know how fast it's changing at the 8-foot mark. So looking through this, I need a formula that relates the volume of a cone to the height of the cone. So this again is an existing formula. I don't know why I'm putting a D here. There we go. That you can go and look for if you don't know them. This one I actually think is kind of easy to remember, because if you know that the volume of a cylinder is pi r squared h, which you should know or be able to figure out, area of a circle times the height of the cylinder. The cone is always 1/3 of that, and that sort of visually makes sense to me that it would be around 1/3. Again, on a test, if I don't provide that formula for you and you need it, you could always say, hey, remind me what the volume of a cylinder is, which means I'll try and be careful to provide it because some of you won't be in the room with me while you're taking this test. So, this is all fine and good, but I have a little problem. I want to relate the rate of change of volume to the rate of change in height. I have zero information about the radius or the rate of change of the radius. If I had dr dt or r information here, I wouldn't worry about this at all. I would just take the derivative, being very careful because this is a function times a function, so you'd end up with a product rule here. But I'm not going to do that here because I don't have any way to get a dRdt or an r to plug in here nicely. I need to figure out how to eliminate the r up front. So I believe this is possible, and here's why. If I'm looking at this picture and I pick a specific h value, I don't get to then pick the r value as well. So r is this radius right here. Remember, this is volume of the water, not the tank, right? The tank is fixed. So once I choose an h, the r is predetermined by the shape of the tank. So I just have to figure out a way to write that down with an equation. What is it about the shape of the tank that predetermines that would allow me to figure out what r is? And this one can be a little tricky for people to spot. One piece of advice I have for you is if you're ever having trouble with a three-dimensional picture, sometimes it works really nicely just to mentally slice it vertically straight down the middle and think about the 2D version. So if you slice the cone straight down the middle, basically the face you'll be looking at, the cross-section, is just a triangle. And we know that the top of this triangle is 10 feet basically. The radius of the circle is 5 feet, so 5 feet on either side. We know that the height is 20 feet. And then we're looking at this r right here and this h right here. So the trick here ends up being similar triangles. We have this bigger triangle right here, and then we have our smaller triangle. Let's see if I have a working color. That doesn't look like anything different in there. And if we look at the smaller triangle, what are we trying to do? We're trying to get rid of the r's. So let's say the ratio of r to h is going to have to equal 5 to 20, which means that r, 5 over 20 reduces to 1/4. R is 1/4 h. So if ever you're looking at a problem, you have too many variables, this is the way I would try and think about that. If I pick the value of h, can I also pick a value of r, or are they somehow tied to each other? And if they're somehow tied to each other, then you should be able to find a formula for that relationship and get rid of one. So back up to here, I have a 1/3 pi, and then I'm going to replace that r with 1/4 h. And this is a little bit nicer. I at least don't have the extra variable, but my advice would be don't take the derivative right now. If you simplify this thing a little, it's going to be significantly easier. So I have a 1/3 pi times 1/4 squared, which is 1/16, h squared times h. I'm going to run out of room. So I have a 1/3, 3 times 16, a 1/48 pi h cubed. And lucky for me, as I get short on room, that's actually really easy to take the derivative of. So we're going to take the derivative of v with respect to t. The 3 is going to drop down in front. 3 over 48 is going to get me back to 1/16. The pi is just hanging out, coming along for the ride. I have an h squared, and I have a dh dt chaining out of that. Let's see if I can fit this in here. Okay, so then I know my dv dt is -2. Know my h is 8, so I now have 1/16. Here, I'm going to put the pi on top. Pi over 16 times 8 squared, 64. dh dt, squeezed in there. Oh, off the edge for you guys. And then I just need to solve. So let's see, 16 goes into 64 4 times. So I need to divide both sides by 4 pi. And then I can even reduce that a little bit more, so I can knock out a 2. So I have -1 over 2 pi. And once again, I'm fine with the exact answer here. I actually like the decimal answer, but since I continue to forget to grab a calculator and I don't really want to use my phone, I'm just going to leave this exact. So I would take either, but units are really important. So this is in the ballpark of -1/6, and this is the rate of change in H, so this should be feet per minute. So the when the water is 8 feet deep, the water level should be dropping by at a rate of roughly 1/6 of a foot per minute. All right, thanks for watching.